Welcome to this video on QR decomposition in Python. In this video, we'll go step by step through the code that implements the QR decomposition algorithm using the Gram-Schmidt process. QR decomposition is a fundamental concept in linear algebra, widely used in numerical methods for solving linear systems, finding eigenvalues, and more. QI decomposition is a method of breaking down a matrix A into two simpler matrices Q and R. Here's what these matrices represent. Q is an orthogonal matrix, meaning its columns are perpendicular to each other and have a magnitude of 1. R is an upper triangular matrix, meaning all elements below the diagonal are 0. Let's dive into the code and see how it works. Here's the function that implements QI decomposition in Python using Numpy. First, we import the necessary library Numpy. It helps us perform matrix operations efficiently. Import Numpy as Numpy. This statement imports Numpy module. Now we define our main function, QR underscore decomposition of A, where A is a matrix we want to decompose. It starts by determining the number of rows n and columns m of matrix A. Def QR underscore decomposition of A, colon, n, m equals A dot shape. We are defining a function QR underscore decomposition using the keyword def, and we are passing the attribute A. Next, we create two empty matrices. The matrix Q will store our orthonormal vectors, and U is used to hold intermediate vectors during the Gram-Schmidt process. Let's start with the first column of matrix A. The vector U, colon, 0 is initially set to the first column of A using the statement U square brackets colon, 0 equals A square brackets colon, 0. We then normalize this vector and store it in the first column of Q. Q within square brackets colon, 0 equals U within square brackets colon, 0 divided by np dot linalg dot norm. And within this we are giving the value U within square brackets colon, 0. This step ensures that our first column of Q is a unit vector, which is an important property of orthonormal vectors. Now we loop over the remaining columns of matrix A. For each column, we start by setting U within square brackets colon, I to the ith column of A. For I in range 1, n colon U within square brackets colon, I equals A within square brackets colon, I. Next, we subtract the projections of U within square brackets colon, I onto all previous columns of Q. This step makes sure that the new vector is orthogonal to all the previous vectors in Q. For j in range of I colon U within square brackets colon, I minus equals to A within square brackets colon, I at Q within square brackets colon, j multiplied by Q within square brackets colon, j. The add symbol in this statement is used for dot product. After orthogonalizing the vector, we normalize it again and store it in Q within square brackets colon, I. Once we have all the orthonormal vectors in Q, we can calculate the elements of the matrix R. The matrix R is upper triangular, meaning it has non-zero elements only on and above the diagonal. R is equal to np dot zeros n comma m for I in range n colon for j in range I comma m, and R within square bracket I comma j equals a within square brackets colon comma j at q within square brackets colon comma I. In this process, we calculate each element of R by taking the dot product of the columns of A with the corresponding columns of Q. And finally, we print the matrices Q and R, which are the results of our QR decomposition. For this, print Q and print R statements are used. A equals to np.array eval of input, and we are calling the function qr underscore decomposition of A. Using eval of input allows us to enter the matrix directly in the form of a Python list, and the code automatically converts it into a MP array. When we run this program, the program will first ask us to enter the array, and when we enter the array and press enter, the program will calculate the Q matrix and R matrix for us. So this first matrix here is the Q matrix, and the second here is R matrix. So using Python language, we have successfully written the code for QR decomposition, and our code execution is successful.